How's it, Chase? Welcome to your last lesson on chapter 5. Today we're going to be talking about the cubic function. Okay, let's get some white here. Okay, so the cubic function is the graph. So this is section 5.23, by the way. Okay, and this is the graph of y equals ax cubed plus bx squared plus cx plus d. Okay, and that is our cubic function. The book says the graph intersects the x-axis at 3 points. Just note that these points can be real or imaginary. Okay, and and it intersects the y-axis at 1 point. And to find these, as with the straight line and all the other graphs, we can let x equal 0 and let y equal 0. Okay, so let's do example 43. Your book jumps straight in. It really doesn't explain things very nicely, but let's do it. Example 43. Okay, and it just says sketch the graph of the following function: y equals x cubed plus minus x squared minus 4x plus 4. Okay, so this is also f of x, right? So what are we going to try to find first? We're going to find our x-intercepts. So to get our x-intercepts, okay, let's do that in red. X-intercepts, let y equal 0. So 0 equals x cubed minus x squared minus 4x plus 4. Okay, so then we're going to factorize, and I don't know if we've actually discussed factorizing of a cubic equation. I'm not going to discuss it now. If you haven't seen how to factorize a cubic equation, you can either find a video on YouTube or just message me and I will get back to you on that and show you exactly how to do it. But for now, I'm going to assume that you know how. So basically, we're going to start looking at values of x. So we're going to say we're going to let's let x equal 1 and see if it's a factor. So what we're going to do is substitute x equals 1 in here and see if the equation is satisfied. If the equation is satisfied, then we know that x equals 1 is a factor of the equation. So 0 equals 1 cubed minus 1 squared minus 4 times 1 plus 4. 1 cubed minus 1 squared cancels, and that is minus 4 plus 4. So we get 0 equals 0. Therefore, x equals 1 is a. So therefore, x equals 1 satisfies the equation. So x minus 1 is a factor. Okay, now that we know one factor, we can get the other two factors by long division. So, also, if you don't know how to do long division of a trinomial, I don't know if we covered it, I actually can't remember. You must let me know. Either I can do a video or you can find a video on YouTube of long division of a a cubic function. So yeah, so we're going to do long division of a cubic function now. So we found our first factor. So we want to divide x cubed minus x squared minus 4x plus 4, and we're going to divide that by x minus 1. So x goes into x cubed, x squared times x squared, and now that I'm doing this, I do remember we have covered it in one of our videos. X squared times x is x cubed. X squared times minus 1 is minus x squared. Okay, swap the signs and add them. So we get x cubed minus x cubed is 0. X squared plus x, minus x squared plus x squared is 0. Okay, and then we're going to bring this one down. So minus 4x. Okay, plus 4. If you can't remember where in the book or where we covered this, maybe just look at the index of your book. I'm actually just going to take a quick look there now. Maybe I can refer you to where we did it. Let's take a look. Sorry about this. I'm just looking in your book to see if I can find it. Let's just check here. Okay, yes. Okay, there's actually a formula for it. No. I lie. I'm lying. Don't let me lie to you. Okay, I can't find it here right now, and I don't want to waste too much time. But it is in your book how to factorize cubic equations. So I'm just going to carry on here. So x goes into minus 4x, minus 4 times. Minus 4 times x is minus 4x. Minus 4 times negative 1 is plus 4. Swap the signs and add. Okay, and that gives 0 and 0. So we're done factorizing. So our factors are x minus 1 and x squared minus 4 equals 0. But we're not done factorizing our equation yet. So one thing, I didn't really mention it, okay? So we're trying to find the roots of this equation. So that's why we're factorizing. We need to find the roots so we can find the x-intercepts. It's the same as with our quadratic function, except now we've got 3, a cubic function. So we're not done factorizing because we've still got an x squared here, so we need to factorize that. So let's just carry this. And this is difference of 2 squares. So it's x minus 2, x plus 2. So now we've got our x-intercepts, which are x equals 1, or x equals 2, or x equals minus 2. Okay, so there you've got our x-intercepts. So those are x-intercepts. And there are 3 of them, as we stated earlier. Intercepts the x-axis at 3 places. Next we need to find our y-intercept. Now to find our y-intercept, what do? We're going to let x equal 0. So y-intercept, let x equal 0. Okay. So let's take our function. So we've got f of x equals x cubed. I'm just rewriting it because it's not on the screen anymore. Minus 4x plus 4. Okay. So to find our y-intercept, we let x equal 0. So f of 0, which is our y-intercept is f of 0 equals 0 cubed minus 0 squared minus 4 times 0 plus 4. And that is equal to 4. So there's our y-intercept. It's at 4. Okay. And they just sketched it just like that. It looks like they didn't get anything else. Okay. Okay. So here is the sketch that you then get from that. One thing to know is the general shape of the cubic. And you're going to see that now. So we've got an x-intercept at 1, at 2, and at -2, and our y-intercept is at 4. And how that graph actually looks is like this. Okay. So there you go. Remember to label your points. Personally, if I were sketching this, you don't have enough information to know exactly how this graph looks. So get a couple more points on the graph to give you the idea of the shape. So either you can do that by substituting a couple of x points into your function and getting the table as we've done previously, or you can generate the table on the calculator and use that just to make sure that the points, like that everything you're plotting is correct. So you could maybe get a point here at x equals -1 and x equals, get a couple of points to make sure that you're plotting the correct shape. Because if you put into your calculator x equals -2 all the way to x equals 3, for example, then you're going to have that point, that point, that point, that one, that one, that one, and that one. So then it becomes clear what the shape of the graph is. Then your book says something interesting. And it says, take note that this graph can also intersect the x-axis twice or even only once, as the following sketch will show. So I'm going to show you the sketch. They've got a couple of these cubic graphs. Okay, I'm a terrible artist. Okay, so the idea is that this is the same graph, just shifted up and down by 1 point. So this is y equals x cubed plus x squared plus x plus 2. This is x cubed plus x squared plus x plus 1. This one is x cubed plus x squared plus x plus 0, or just plus x, like that. Okay, so all that's changed is your plus d, which is your vertical translation. It moves the graph up or down, that plus d, as you'll remember from your straight line graph and your parabola. That last term, the constant term in your general form. Let's see if I've got it here somewhere so that I can actually show you. Okay, here. This last term, the constant term in your equation, in any function, just moves the function up or down. If it's positive, moves it up. If it's negative, moves it down. So that's what we've got here. Now, didn't we say earlier that it intercepts the axis at 3 points? And now, I've drawn you this sketch, and I'm saying, but it can, and your book is saying it can only intercept once, because you'll see here, this graph, this first one, intercepts the x-axis only once. Then you've got this graph, which intercepts once there and over there, which is twice. And then you've got this graph, which intersects 1, 2, 3 times. But we said it intersects the x-axis at 3 points. That's why I added here real or imaginary points. What happens with this, the first graph, your other 2 x-intercepts exist, but they're going to be imaginary points. Here you've got one imaginary intercept, and there all your intercepts are real. Okay? So what do I mean imaginary intercept? Well, if you take, for example, your equation, and you got to this point, so you get to this point here, you've got x minus 1, so you've got one factor. But what happens if your second equation was in the form x minus 5x, for example, plus 7? Okay? This can't be factorized. If you use x squared. Okay? So if you got this and you need to break this up into 2, you can't factorize it in your head. You would have to use you'd have to use the quadratic formula, negative b plus minus the square root of b squared minus 4ac over 2a. Okay, now this can give you imaginary roots. For example, this isn't the roots for this equation. You could end up with x equals 5 plus j2 and x equals 5 minus j2. And those are your imaginary intercepts, i.e. the intercepts which you can't, so that, or I lie, but basically it tells you where your x-intercepts are on this graph that looks like it only has one intercept. I know this is a difficult concept, but this graph only has one real x-intercept, and that is over there. You can see it. Nowhere else does it intersect the x-axis. But it's cubic, and therefore it must have 3 intercepts of the x-axis. It's just that the other 2 x-intercepts are imaginary. Okay. And this brings us to the last piece of chapter 5. At last, we're done with chapter 5 after this. 5.24. Sketch a cubic function using differentiation. Okay, now there's this one thing I forgot to add. A cubic function can have 2 kinds of shapes. It can either look like this, kind of like a sinusoid, except it only goes up and down once and then continues straight. It can also look like this. Okay, so it comes up and it starts like it wants to turn and go down, but it never does, and then goes back up again. Those are the 2 shapes of your cubic function. Just so you know. So it can look like either one of these 2 when you sketch it, either using a table or whatever method you decide to use. Okay, section 5.24. Let me actually get us a new page for this. Okie dokie. 5.24. Come on. Trying to get... Sometimes this thing doesn't work when you try to change colors. It's very irritating. Okay, section 5.24. Okay, sketching a cubic function using differentiation. Okay, so let me read what your book says. With the aid of differentiation, we can draw a third power function without using the table method, which is tedious. By equating the gradients of the turning points of a cubic function to 0, the points can be easily obtained. So basically, what they're trying to say with that whole story is that if you've got a cubic function that looks something like that, okay, how at this point, right here, this turning point, and at that turning point, and this applies for the parabola too, by the way, at the turning point, the gradient is 0. M equals 0 at that point, and at this point, M equals 0. Because you can see it's sloping upwards, 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 so it's got a positive gradient. Now, it's completely horizontal at that point. So gradient is 0, and then the gradient goes negative, and then gradient is 0, and then the gradient is positive. So, we can find the turning points, and then we can find the roots. Okay. So they say Oh, by the way, the gradient is 0 where dy by dx equals 0, i.e. the derivative equals 0, but we know that the derivative is just the gradient. So, example 44 says, draw f of x equals x cubed minus 3x by first calculating the turning point, then the roots, then the y-intercept. So how do we get the turning points? That is, the turning points are where dy by dx equals 0. So first, let's take dy by dx, or f prime. So f prime of x equals, and I'm not going to talk about how to differentiate now if you don't remember, like we're covering that in the next section anyway. So f prime of x equals 3x squared minus 3. Then we say, and f prime is the same as dy by dx. Then, to get the turning points, so to get TP, let the gradient equal 0, or let f prime of x equal 0. So we've got 3x squared minus 3 equals 0. And now all we have to do is solve for x. So how are we going to do that? Well, we can divide the whole equation through by 3, which leaves us x squared minus 1 equals 0. And then we've got a difference of 2 squares. So x minus 1, x plus 1 equals 0. Okay, so our two turning points are x equals 1 and x equals minus 1. So there are our two turning points. But this, you'll see, this is not the full point, right? This is just the x point. So to get the y point corresponding, because we want the ordered pair where the turning point is, we substitute these x values back into our function to get the corresponding y point. So we calculate f of 1, which is equal to 1 cubed minus 3 times 1. So I just substituted 1 into our original function, equals 1 minus 3 equals minus 2. So our one turning point is at the ordered pair 1 and minus 2. And for our other ordered point, we calculate our other turning point ordered pair, we're going to calculate f of minus 1 equals minus 1 cubed minus 3 times minus 1, which is negative 1 plus 3, which is equal to 2. So our second turning point is at the point minus 1 and 2. So now we've got our two turning points, and we're very happy about that. Next, they say calculate the roots. Okay, so the roots I'll do in red. How do we calculate the roots? The roots are also known as the x-intercepts. How do we get an x-intercept? We let x-intercepts, so let y equal 0, or f of x equal 0. So we take our f of x and let it be equal to 0. So x cubed minus 3x equals 0. Okay? And now we have to so we've got x cubed minus 3x equals 0. So now we have to factorize this equation to get our 3x points. So let's factorize the equation. So remember, for factorizing, common factor, difference of two squares, then trinomial, and then cubic. So those are things, well, not even. We're looking for common factor, difference of two squares, and then trinomial in that order. So is there a common factor here? Yes. We can take out an x, which leaves us with x squared minus 3 equals 0. So now we can factorize this bracket. And this bracket, I just want to see how your book did it. Okay. Your book did it that way. This is not a difference of two squares because 3 is not a square number. So let's factorize it as a trinomial. So we're going to use the quadratic formula. So we're just factorizing this piece now. I'm going to actually do it in a different color. We're factorizing this piece. So x equals negative b plus or minus the square root of b squared minus 4ac over 2a. b is the coefficient of the x term, which is 0 because there is no x term. So it's equal to negative 0 plus or minus the square root of 0 squared minus 4. A is the number in front of the x squared, which is 1. C is the constant, which is minus 3, over 2a, which is 2. 2 times 1. So that leaves us with plus or minus the square root of 0 squared is 0. Minus 4 times minus 3 is 12 over 2, which is equal to plus or minus what is the square root of 12? Square root of 12 is 2 root 3. Just do it on your calculator, over 2. So plus minus root 3. Okay? So now we've factorized this equation fully. So let's go back to it. We've now got x into, and now we factorized that second bracket into x plus root 3, x minus root 3 equals 0. So x equals 0 or x equals minus root 3 or x equals root 3. So now we've got our two turning points and we've also got our roots. Next, find the y-intercept. We'll do that in blue. So we're going to find the y-intercept. To get the y-intercept, what do we do? Let x equal 0. So if f of x is, this is just the original f of x that we were given. F of x was x cubed minus 3. So if we let x equal 0, oh I lie, minus 3x. Okay, so f of 0, which is our y-intercept, is equal to 0 cubed minus 3 times 0, and that is equal to 0. So what do we now know? We know everything we need. We know that our turning points are at, what were they? 1 and minus 2, 1 and minus 2, and minus 1 and 2. So there's our two turning points, 1 and minus 2, minus 1 and 2. Our x-intercepts are at the points 0, 0, minus root 3, 0, and root 3 and 0. Okay. How did I know that? So we've got the x points. How do I know that the second coordinate is 0? Well, it's the x-intercept, and the x-intercepts are on this line, and these for the x-intercepts, y is always 0. So that's how I got those points. And then we also know y-intercept, which is at y equals 0. So it's at 0, 0. Once again, how do I know that the x coordinate is 0 here? Well, I let x equal 0 when I substituted in, and I got y equals 0. So I was just calculating an ordered pair with x equals 0, and I found that y equals 0. So there's my 2 points. So now I can very easily sketch this graph. So let's do it. We just plot our points and we sketch it. So I'm going to do those in red, there, and there. Okay, so we've got our axis system. So let's sketch in our turning points in red. So we've got 1 and minus 2, so x is 1, y is minus 2, so that is somewhere there. Once again, you should label all of these very nicely and draw out all of your markings and label everything. I'm just doing this quickly for us. So this is the point 1 and minus 2. Then we've got the point minus 1 and 2, which is minus 1 and 2. So there's our two turning points. Next, I'm going to draw in our x-intercepts, which are 0, 0, which is here, minus root 3 and 0. Now, if you don't know, minus root 3 is negative 1, 7, which is roundabout here. And then we've got root 3 and 0. Root 3 lies more or less over there. Okay. And then we've also got our y-intercept, which is at 0, 0, same as our x-intercept. So let's join up the dots. Remember, it turns at the red points. So we go there, go through and turn. Then we go down and turn and up. And I think I made a mistake with the 1 point. Yes, I did. This green point here is wrong. Sorry about that. Root 3 lies over here. Because this red dot is at the point 1. So that is 1. So 1,73 is here, which is our other x-intercept. So there you go. You've sketched your graph. Remember to draw in your points, label them. So this was minus 1,73 or minus root 3. This point is, this is our turning point, minus 1, 2. You get the picture. Label all the points you calculated, draw out your grid lines nicely, label the x and y axis, etc. Okay, and that brings us to the end of chapter 5. Next video we're going to go on to differentiation, and we're going to start rushing to get you done with this syllabus. But what I am going to do now is, you asked me a couple of questions a few days back on WhatsApp, and they just came to mind now. I completely forgot about them up until now. So, but anyhow, let me quickly find your questions and I'll answer them. Okay, so you asked me some questions from a past paper. Okay, so your past paper questions. Let me just. So these are the ones you WhatsApp to me from your past paper, and I'm quickly going to we'll just take a quick look at them. So question 1.1.1 said, sketch the graph of x squared over 72 minus y squared over 32 equals 1 over 2. Now, from this form, this is actually a hyperbola. Yes, hyperbola. Okay. A hyperbola has the general form x squared over a squared plus minus, if that was a plus it would be an ellipse, but it's not, minus y squared over b squared equals 1. And where this is your x-intercepts, and this is your y-intercepts. And it's centered at 0, because that's what this general form assumes. So let's just get this into that form quickly. So I want a 1 on the right hand side. So if I multiply through the whole equation by 2, then I'll have a 1 on the right. So I get 2x squared over 72 minus 2y squared over 32 equals 1. Then I simplify these fractions. 2 over 72 is the same as 1 over 36. So x squared over 36 minus 2 over 32 is 1 over 16. So y squared over 16 equals 1. So now we know that a squared, from our general form, a squared equals 36, b squared equals 16. Therefore a equals plus or minus root 36 equals plus minus 6, and b equals plus or minus root 16 equals plus or minus 4. So now we know our x and y intercepts, so we can just sketch it very easily. And this is a... I lie. Yes, this is the hyperbola. I think it's called the... Just want to quickly check the term for it in your book. I can't remember the term they used for it. Yes, here we go. This is your non-rectangular hyperbola. Okay? So I lied. This is not your y-intercepts for the non-rectangular hyperbola. Okay? You just get your x-intercepts. So we know that our x-intercepts are at plus minus 6. So that is here. Minus 6 plus 6. We also know from this form of the non-rectangular hyperbola that it has asymptotes at y equals b over a x, and that is plus minus. So you can sketch in your asymptote lines, which are b over a, which is this line here, and we've got this line here, which is minus b over a. So this would be plus, so this line is b over ax, so it is 4 over 6x, and you must label it. This line is minus 4 over 6x, and we've got our intercepts, and our hyperbola just lies in between there, like that, and there, like that. Okay, so that's the first one, done and dusted. Let's see what your next question was. Okay, so they asked what is the domain of this graph. Now if you look at the domain, the x values, can you see that the graph includes all values of x up to minus 6, and then it includes the values of 6 and onwards. So the domain is minus infinity to minus 6, including minus 6, because it crosses that minus 6 point. Then it doesn't include minus 6 to 6 at all. And then it starts again at 6 and goes on to infinity. So 6 to infinity. Okay. And we can just say and. Okay. Then the next question is the graph in question, okay, it's a bit cut off, but it says, is it symmetrical? Well, that's what I can gather. Yes, it is symmetrical about the y-axis, because if you fold the thing above about the y-axis, you'll see these two lines are going to lie on top of each other. And I can't answer 1.1.4 because I can't see it. Then you said, then the next question there, which I don't know what the number is, it says sketch x equals minus root 20 minus y squared. This is an inverse function for something, but what I would do is write it in the form of y equals x of some sort, okay? Because that's how a function is written. So let's do that. So we've got, take the minus across, that gives minus x equals root 20 minus y squared. Then we're going to square both sides, so we've got x squared equals 20 minus y squared. Then we've got x squared plus y squared equals 20. And what is it? It's a circle. So you've got because this is in the form x squared plus y squared equals r squared, where r squared equals 20. Okay. So now we've determined that this is a circle, because we've gotten it into that form. So we know it's a circle. But this is only a half circle. Because, yeah, if you go rewatch the video on circles, you'll see that this is just a half circle, because now we've written it in the form of a function. Even though it's written in the form x equals something, something, this is a half circle. So, how are we going to draw it? Well, usually the half circle is written in the form y equals negative root r squared minus x squared. Okay, this sign in front tells you whether it's the negative half or the positive half. Okay, so this is the negative half of a circle. Okay, but now this one's written in the weird form, which is x equals blah blah blah. So how are we going to draw that? Well, it's just going to end up looking like this. Okay, there's your half circle, and it's going to have a radius, because we know from the form here that 20 is equal to r squared, so r squared equals 20, r equals root 20, plus minus, but a radius can't be negative, so it's just plus. So this value here is root 20. This is root 20, and that is minus root 20. Because it's the radius of a circle, and the circle is obviously centered at the origin. So there you go. Instead of it, if it were written in the form y equals blah 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 minus x squared, then we would have had the negative half there. But it's written in x equals y form, so it's the negative half on the x side. And there you go. Another interesting way, and I'll say this and just end off the video here, another interesting thing that you could have done here is simply write this as y equals minus root 20 minus y squared, or minus x squared, sorry. Okay, so you could have just written it like this. So we just swapped the y and x again, and you know how to draw that. That's going to look like this. Okay, and then you just tell them, well, I'm swapping my x and y axis. So usually you would have x, y, but because you swapped x and y in the function, if you just swap x and y in the graph, you will have done the same thing. So tell them, that's my x-axis, that's my y-axis. Whether your lecturer will accept that or not is a different question, but it is perfectly valid just to do that. And I just wanted to let you know as well, if you're battling to draw these graphs, I'm curious if Microsoft Math can do it. Let's try Math. Okay, Microsoft Mathematics. So let's just test if Microsoft Math can sketch these. I don't think it can sketch that first one because it's a relation and not a function, but we're definitely going to try. Let's see what it can do. X squared over 72 minus y squared over 32 is equal to 0.5 or 1 over 2. So let's see, I don't think it's going to graph that. No, it couldn't graph it. Okay, because it's written in as a relation and not as a function, that's why it couldn't. So if you solve this in terms of y, then it would be able to plot half of it. Okay, But what it can do is it can definitely, well, I'm fairly sure it could plot your second equation, which is x equals minus 20 minus y squared, and that we need to take the square root of that, which is the same as going to the power of 0.5. Okay, and let's see what that does. Let's see if it plots it. There you go. And there is your half circle. I believe it is actually a circle. It's just our plotting range is messed up. So if we go minus 8 to 8 and minus 8 to 8, you'll see that it's a half circle. There you go. There's your half circle. And there is your radius, your x-intercept at negative 4.5 almost, which is root 20. Okay, and there you have it. There's the answers to your questions. Yeah, try use Microsoft Math. If you don't know how a function looks, feel free to graph it on Microsoft Math or use the table function on your calculator. One thing I wanted to add earlier, for factorizing, you know, if you have to factorize cubic, so ax cubed plus bx squared plus cx plus d, or a equals 0, if you have to factorize that, or if you have to factorize ax squared plus bx plus c equals 0, your calculator, if you get the Casio FX991ES or any of the FX991s, it can actually factorize this equation for you. If you just press, if you go mode, and then I think you press, I don't have my calculator with me, mode, factor, and then, yeah, what I'm going to do is, because I don't have my calculator with me, I'll just do some research for you here. Okay, so I just did a quick Google search, and there are videos available on how to solve quadratic and cubic equations using the FX991. So there you go. So you press mode, then you go to equation, and then it gives you the various forms of the equations over there. So there is your ax squared plus bx plus c equals 0, or your ax cubed plus bx squared plus. So you can select one of those modes by pressing 1, 2, 3, or 4. And then it's going to ask you to enter a, b, and c, which are the coefficients of the, the coefficients of your equation, a, b, and c, or a, b, c, and d if you've chosen the cubic mode. And once you enter them, it'll actually give you your x values, and then you just press the replay button, I think left or right or up and down, and it'll give you x1, x2, x3, which are your 3 roots. So if you get this calculator, your calculator can give you those roots. Your teacher is going to want you to get the roots yourself manually, the proper way, but this is a great way to check your roots. So yeah, thanks for watching, Chase, and yeah, I'll see you next time we can start differentiation. Cheers.